Good day everybody. In today's class we will learn how to integrate this integral 0 to infinity e raised to the power of negative x squared times cos of 7x dx. This is a complex integral, or when I say complex I mean to say this is a difficult integral to integrate. So what we will do is we will use the technique popularized by Feynman. So having mentioned Feynman, we would apply the technique. As I always mention that this technique was initially developed by Leibniz but popularized by Feynman. Now the idea is to define a function. So the reason that we are defining the function is to ensure that we are able to remove the complexity level of this integral. So when we are defining a function, we have to make sure that the function defined is able to reflect the given integral. That is the entire idea. So let me define this function. Let f of u be equal to integral 0 to infinity e raised to the power of negative x squared. I'm going to write this as cos of u times x times dx. Now u is the variable here, which takes the value 7, and that would result in the given integral. So what I'm going to do now is I'm going to be differentiating both sides. So let me differentiate both sides with respect to u. So let me write that differentiating with respect to u, we get. So this is going to be, let me write that down here, d over du of f of u is equal to d over du of integral 0 to infinity e raised to the power of negative x squared cos of u x times dx. Now clearly you can see that u is a variable and x is a variable. So if you were to push this d over du inside, it will become partial derivative. So let us do that. Integral 0 to infinity dou over dou u of e raised to the power of negative x squared times cos of u x times dx. Now e raised to the power of negative x squared is a constant, so I can literally take that out of the partial derivative. So let me write that down. E raised to the power of negative x squared times dou over dou u of cos of u times x times the dx. The limits are 0 to infinity. So this is equal to integral 0 to infinity e raised to the power of negative x squared. We have to differentiate this with respect to u. So differential of cos is going to be negative sine of ux. Now the coefficient of u is x, so we need to place that x here, times dx. So this is what we've got. Now let me rewrite this in this fashion. This is equal to integral 0 to infinity, I have a negative sign, let me place that there, x times e raised to the power of negative x squared sine of u times x times dx. Now we will apply integration by parts. On the left hand side, d over du of f of u, I can write that as f dash of u. Okay, coming to this part, we will use the concept of Lie. So I got actually a trigonometry function preceding before the exponential function. Now what I wish to do is I would like to club these two quantities as my dv for the simplicity in the integration. Of course it has got 3 terms, so I will club these 2 terms and I will take it as x times e raised to the power of negative x squared times dx. This is my dv, and my u is going to be sine ux or sine of ux. Right? So if I were to differentiate this du, on the right side this is going to be cos of u times x into the coefficient of x is actually u, right? So we place that u there, and then differential of x is going to be giving me dx. So this is what I get for du. Now integrating this, let me take x squared to be equal to sum t. This is going to be 2 times x dx is equal to dt. So x dx is equal to dt divided by 2. So let me use the space here. So integral x times e raised to the power of negative x squared dx is equal to integral, in place of x dx we substitute dt, there is a 2 there, so place it as 1 over 2 times e raised to the power of negative t. So if I were to integrate this, this is going to be e raised to the power of negative t with a negative sign, will the 1 over 2 constant. This can be rewritten as negative 1 over 2 e raised to the power of x squared, right? T is x squared, but there's a negative sign. So this is what we get for v. Now let me use the integration by parts formula. So uv negative integral v du. On the left hand side I've got this entire integral. So this integral is rewritten like this. So this is equal to my u. What is my u? My u is sine ux. My v is, let me write it like this, 1 over 2 times, now e raised to the power of negative x squared, I can push it to the denominator. So this is going to be e raised to the power of x squared, and the limits are 0 to infinity. So 0 to infinity, place the limits. The negative sign is there, negative integral v du. So negative negative, I would have a positive sign. This is going to be positive, and integral v du is going to be 1 over 2 times, my v is e raised to the power of negative x squared, my du is u times cos ux times dx. We got to place that, so let me just place that value, u times cos of ux times dx. Limits are 0 to infinity. Now I can take the u out because the integration is with reference to x. So this is rewritten as 1 over 2 times sine of ux divided by e raised to the power of x squared. Limits are 0 to infinity. Positive 1 over 2. I got a u, so let me write that as u over 2, and then I got the integral sign 0 to infinity e raised to the power of negative x squared times cos of ux times dx. Now on the left hand side, what do we have on the left hand side? See, on the left, this is what we have got on the left hand side, right? This is the term we have to integrate, and we have integrated it. So let me write that term down. Okay, let me just place the value 0 to infinity x times e raised to the power of negative x squared sine of ux times dx. So this is what we have to integrate, and we have got the value here. Now if I were to apply the limits, I have to allow x to tend to infinity. When x tends to infinity, e raised to the power of infinity is in the denominator, so that's going to be 0, and the lower limit sine of 0 is also 0, so this entire term will vanish. So we are left with u over 2 integral 0 to infinity e raised to the power of negative x squared cos of ux times dx. This is what we are left with. For what? For integral 0 to infinity x times e raised to the power of negative x squared sine of ux times dx. Now if you head back to our initial definition of f of u, you see that what is f of u? F of u is integral 0 to infinity e raised to the power of negative x squared cos of ux times dx. So what we have got? We have got integral 0 to infinity e raised to the power of negative x squared cos of ux dx. So this is equal to u over 2 times f of u. And on the left I got 0 to infinity x times e raised to the power of negative x squared sine of ux times dx. So this value is obtained. Now let me take that value. Let me write this as 2. I'm taking this value and I need to substitute it here, right? So f dash of u will be equal to this quantity, negative of u over 2 times f of u. So let me write that down. So therefore 2 is rewritten as f dash of u. Let me write that down for you. F dash of u is equal to negative x times e raised to the power of negative x squared sine of ux times dx. Now this is equal to this. So this is equal to negative u over 2 f of u. Now what is this? This is nothing but an ordinary differential equation. So I can rewrite this as f dash of u is equal to negative u over 2 of f of u. Now this can be further rewritten as f dash of u is going to be df over du is equal to negative u over 2 with f. Now I can bring the f down and write this as df over f is equal to negative u over 2, right? All I'm doing is using variable separable method. By variable separable method, you bring the f down, you move the du out, right? You move the du across. I have done a whole lesson on differential equation, the complete topic on differential equation. I would like to request you all to watch the video. So by variable separable method, move f down, move du out to the top right. So this is what we get. So we can integrate both sides. Upon integration, this is going to give me ln of f and this is going to give me negative u times du. When you integrate, you get u squared divided by 2. It's going to be u squared over 4 positive. Let me have this as c1. Now why do I take c1? Because there is going to be a constant when I get rid of the logarithm. This is actually to the base e. So I can rewrite this as f is equal to e raised to the power of negative u squared divided by 4 positive c1. Now from the law of exponents, if you have something like this, a raised to the power of m positive n, you can rewrite this as a raised to the power of m times, e raised to the power of m positive 1, m positive n can be written as e raised to the power of m times e raised to the power of n. That's exactly what I'm going to do. I'm going to rewrite this as e raised to the power of negative u squared divided by 4 times e raised to the power of c1. This is a constant. So I can rewrite this as e raised to the power of negative u squared divided by 4 times c2. So now you know why I have taken this as c1. Now this is my function f. So we are almost done. Just within a couple of steps we would be able to arrive at the solution. So let me go to a new page. Now we have got f to be equal to e raised to the power of negative u squared over 4 times c2. But we have defined f of u to be as integral 0 to infinity e raised to the power of negative x squared cos of u times x times dx, right? So comparing this with this, or I would say equating both, we get. So what do we get? This is going to be integral 0 to infinity e raised to the power of negative x squared cos of u times x times dx is equal to e raised to the power of negative u squared over 4 times c2. Now let me take, I want to get the value of c2, right? Without the value of c2, we wouldn't be able to arrive at the final solution. So let me take u to be equal to 0. If u is equal to 0, cos of ux is nothing but cos of 0 times x, which is nothing but cos of 0, which is equal to 1. So this is going to be 1. So I get 0 to infinity e raised to the power of negative x squared times dx is equal to e raised to the power of negative u is 0. So this is going to be 0 times c2. So e raised to the power of negative 0 or e raised to the power of positive 0, both will lead us 1. So you get c2 on the right hand side. Now what is this? This is nothing but Euler-Poisson integral, the famous Euler-Poisson integral. And this as a value For, let me state that integral. For integral negative infinity to infinity e raised to the power of negative x squared times dx. So this is the famous Euler-Poisson integral. I will also prove this integral in the oncoming class. So this is from infinity to negative infinity to infinity, and this is an even function. So this would mean, therefore, 2 times integral 0 to infinity e raised to the power of negative x squared dx is equal to root of pi, which would imply 0 to infinity e raised to the power of negative x squared times dx is equal to root of pi over 2. So I can take this value and substitute it here. So what I wish to do is, I would take this value and I will place this here, root of pi over 2. So this means, let me write it properly, C2 is equal to root of pi over 2. So if I were to take this as 3, take the value and place it here. So all that we need is to solve this, right? So therefore 3 becomes, let me write that down, therefore 3 becomes integral 0 to infinity e raised to the power of negative x squared cos of u times x times dx is equal to e raised to the power of negative u squared divided by 4. C2 is root of pi over 2. So I can write that down. But we need, what do we need? We need u to be equal to 7. So this would mean integral 0 to infinity e raised to the power of negative x squared cos of 7x, this is what is given, right? This is what is required, is equal to e raised to the power of, u is 7 squared is 49 divided by 4. I have a root of pi here and a 2, right? So this is the solution for this beautiful question. Thank you everybody. I hope you enjoyed this question. Please subscribe and like and share. Have a good night.